Hi, welcome to this module. In the last module what we have seen how can we do the bonding of two wafers. In fact, we have taken an example of a microfluidic system where you used soft lithography to create a mold and to use the mold with PDMS and form the channels within PDMS, right. So, using that PDMS and a glass, we kept that glass and PDMS in an oxygen plasma system, and after that you take it out and bond it using a external force to create your microfluidic platform. Now, when we talk about micro, there is a system called micro electromechanical systems, which is also called MEMS based systems, alright, and lot of sensors that we will be discussing here or actuators that we will be discussing here are based on MEMS based technology. So, what are these MEMS and where are these MEMS used? So, these MEMS are used in smartphones, tablets, camera, gaming devices and lot many applications. So, if you see the slide, these smartphones like you see here, they are, like I said, smartphones, tablets, cameras, gaming devices, and you can see a module in which you will be able to see there is an antenna switch module, there is a transceiver module, there is a sensor module, low power FPGA module, accelerometer is there, audio codec is there, then there is a tuner and demodulator is there, controller is there, right. So, advanced voice processor, transmitter, power management, biosensors. So, if you see this particular chip, you will be able to recognize and understand the beauty of a MEMS based technology and how we can miniaturize the entire system into the few microns technology. And in fact, right now there is a few nanometer technologies going on for fabricating MOSFETs, but when we are talking about a sensor, it is little bit different than MOSFETs. However, this consist of all the things together, and there are several companies which are working on this particular domain. Qualcomm is one of the companies which extensively uses the transceiver, transmitter and lot of other electronic components, while the biosensor is used from the pulse oxy IC, where you have where the other things are from the different companies like InvenSense, and this is what is there within the Samsung Galaxy S5. So, if you talk about S10, it would have even advanced version of this kind of sensors. Now, when you talk about MEMS based operation or MEMS based sensors, that means that anything that is related with micro machining. If I am using a micro machining technology, then it is called MEMS based technology. So, three types of transducers are there: capacitor transducers, piezoelectric transducer, thermal transducer. Now, generally you have capacitor. If I write the formula of capacitor, Kc equals to Ka epsilon naught upon D. Right. So, this K is a constant and dielectric constant, A is your area, epsilon naught is a permittivity and D is your diameter. If you change the diameter, the capacitance would change. If you change the area, capacitance would change. If the permittivity will remain, dielectric constant will remain constant for a given material, but if you change the material, dielectric constant will also change. That means that if I change the size of this of the fabrication, my capacitance would be affected. Same thing if I want to talk about the distance. When I say size, means either I can change the distance or the area, depending on I can change the capacitance. Another point, that is piezoelectric. Piezoelectric is where, see, there is a very distinct difference between piezoelectric and piezoresistive. If I say piezoresistive, then what does that mean? Piezoresistive components are components where when we apply a pressure or a force, there is a change in resistance. Alright, these are piezoresistive. In case of piezoelectric, when you apply a pressure, what will happen? There will be a change, the output will be in terms of few volts. There is change in the electrical output, or vice versa. In piezoelectric, if I give the electrical signal, there will be change in the force. Okay. So, that is a piezoelectric material, where thermal is when you apply a thermal energy, it will change the shape. For example, there are SMAs which are smart actuators, and finally, there is a microfluidic platform that we will be discussing lot in the screening technologies. So, here you can see that when you have a sample introduced junction, right, and electric field is applied across the channel, moves the sample into separate column. This is a microfluidic thing. right, and finally different components of samples are prepared due to different electrophoretic mobilities. This is more like a droplet formation. We will discuss it about this particular device if time permits later. However, you can see here these are thermo actuated micro cantilevers. That means when we apply heat, it will actuate and it will start bending, right. So, this is thermo actuated micro cantilevers. We also have the drives where you have a sensing electrode, you have a annealing and bias electrode, and you have a drive electrode. When you operate it, this drive will move in this particular fashion. You see there are these finger electrodes, all right. These finger electrodes are there. Now, when I am applying this voltage, what will happen? This drive would move further like this. So, you see the distance between here and this one, this is covering that space, right. So, that is it is a movement, this movement of 1 and 2 is in this particular direction. When I change it, it will come back, right. So, we are moving these fingers, you are moving these fingers, is not it. So, that will that depends on how you apply the external energy. So, again this is fabricated using micro machining. We will be talking about more on a sensing part at some point of time. So, you will understand how we can fabricate this kind of interdigitated electrodes. These are nothing but fingers, right. So, if you see these are individual fingers here like this, correct, and then when you apply, these fingers will move. Same thing here also, right, this one, these are fixed one, right, or these are movable one, and this internal one is fixed one, right. So, when you apply a voltage, this will move and this guy will move, all right, it moves towards this direction and comes back. So, same thing goes for here. You see there is a diaphragm, right. So, if I have a diaphragm and if I apply a pressure, then there is change in the resistance. For example, if I take a silicon wafer and I grow oxide, which is my thermal oxide, which is silicon dioxide, SiO2. Now, on this silicon dioxide, I have a strain gauge, all right, strain gauge. These are the contact pads of strain gauge. These two are contact pads of strain gauge, and this one is your strain gauge, all right, and this one is your oxide layer. Right. Now, what is this? This is silicon wafer, right. So, silicon is hard material. If I apply pressure, it will not bend. If I apply a pressure, it will not bend. So, what should I do? I have to create a diaphragm. For this, I had to create a diaphragm. So, for creating diaphragm, we will do a micro machining step, micro machining. So, for that, what we will do? Let us take this example. I will just draw it here. So, you understand, you see this thing, right, and what we want is a micro machined or diaphragm. So, what we will do? We will create a diaphragm. We have strain gauge on an oxidized silicon wafer, contact pads, right, contact pads. And contact pairs for what? For your strain gauge, for your strain gauge. Alright. Now, if I apply a force here, this silicon will not bend, right. So, I need to create a diaphragm. What I want is, I want a diaphragm like this, so that when I apply a force, this will bend, is not it? This would, if I apply a force, this should bend. That means bend like this. Alright. So, when it bends, what will happen? Because of the strain, there will be change in resistance. Because of the strain, there will be change in resistance. Right. So, if I measure the resistance across this one, this will be R. If I measure across this one, there will be R plus delta R, depending on whether it is compressive stress or not. All right. So, for if I apply force on this, there will be minimum change because the silicon is hard. So, I have to fabricate this particular design. That is what is shown here, right. You see here, there is a bending that is caused because of the application of a voltage, right, and because it is a piezoelectric actuator. So, apply a voltage, it will show change in pressure. That pressure will change, it will bend, but this bending is only possible when you have your micro machined sensor based on MEMS based technology. Right. So, the point is, how can we fabricate this sensor, right, this one. So, you know how to do it, right, all of you know, right. Let's do it together. So, you will understand what we will do. First thing is, we after fabricating this strain gauge, how to fabricate a strain gauge? Very simple, no, fabricating strain gauge. See, you take oxidized silicon wafer, all right, take oxidized silicon wafer and then coat a material that is used for your strain gauge. So, this is your material for strain gauge. Next step is, you will spin coat, what? Photoresist, right. So, you will spin coat positive photoresist. Okay. Then next step would be soft bake, right. Next step would be loading a mask. Mask would be bright field mask, right, bright field mask. So, wherever the region of photoresist that is not exposed, the region of the photoresist which is not exposed will get stronger, right. We have already studied that when we take positive photoresist, the area which is not exposed will get stronger. What is this? This is my bright field mask. right. Next step would be UV exposure, UV exposure. Next step would be photoresist developer, right. If I dip this wafer in photoresist developer solution, what would I have? I would have my oxidized silicon wafer with my material for strain gauge, and on that I would have photoresist protected where it was unexposed, right. So, this is my photoresist, this one is my strain gauge material, this is SiO2 silicon SiO2. Next step would be I will dip this wafer, I will perform hard bake, right, hard bake and then dip this wafer in etchant for the strain gauge material, right, etchant for the strain gauge material. So, if I dip the wafer in the etching solution that will etch the material of the strain gauge, what will I have? I would have this pattern, correct. So, you can see that photoresist, wherever there was photoresist, the material below the photoresist got saved, it did not get etched. This is photoresist, the material below photoresist is saved, right. So, what is the next step? After this, next step would be I will dip this wafer in acetone. So, if I dip this wafer in acetone, photoresist will be stripped off, and what will I have? I would have my oxidized silicon wafer with a strain gauge. I would have my oxidized silicon wafer with strain gauge, right. But again I want this wafer and not this one, is not it? I want this pattern and not this one. So, what will I do? I have to perform a further photolithography to obtain this pattern, right. So, what is the step? So, let us see. So, this you understood, right. We will just quickly repeat. You have oxidized silicon wafer, you have your strain gauge material, you deposit using one of the techniques either PVD or CVD. PVD is physical vapor deposition, CVD is chemical vapor deposition. On that you spin coat positive photoresist. On after that you have to do soft bake, which is at 90 degree, right, 1 minute hot plate, followed by a bright film mask, and then you expose it with UV. The area which is not exposed will get stronger when you develop the wafer in a photoresist developer. So, you can see this particular pattern. After that you have to dip this you have to perform a hard bake at 120 degree centigrade, 1 minute hot plate, and then you have to dip this wafer in a etching solution for strain gauge. When you do that, you will have this particular pattern, right, and then you have to remove the photoresist. That means you have to strip off the photoresist. When you strip off the photoresist, what will happen? You will have the strain gauge formed in this particular fashion. So, I will rub this one, and we will now form the diaphragm, right. Diaphragm we will form using micro machining technique. Which technique? Bulk micro machining. How many techniques are there in micro machining? Surface micro machining and bulk micro machining technique, right. So, we will use bulk micro machining technique, right. So, in bulk micro machining technique, and what we have to do here, we have to etch. First is BHF, first is silicon dioxide using BHF, and second one is etching silicon. Silicon is etched using, if it is wet etching, it is etched using KOH or TMAH, or if it is dry etching, then we will use the SF6, right, and CF8, where we will use the DRI, right, CFX and SF6 for DRI to etch silicon. So, now let us assume that we have the strain gauge, on the oxidized silicon wafer, right. So, I will just draw here, this is our strain gauge. I am just making this bold, right, this box bold to help you out to understand that this is the actual sensing layer, and these are two contact pads which are not bold, just for that. Otherwise, everything is same material. You can also use the gold contact to take out the final contact pads, but that we will discuss later. Now, on this you have to form this one. So, what you will do? You will spin coat photoresist on front and you will spin coat photoresist on back, alright. You will spin coat photoresist on front or back, or in fact, if you know that the material on the front, this material will not get etched in a photoresist in photoresist developer, then you can just leave it like this. So, now you have photoresist here. So, I would do a front to back lithography. That means that you need to know where you want to etch on the back side. This is the front side of the wafer, this is the back side of the wafer, right, back side. So, what you have to do perform? You have to perform front to back lithography, front to back alignment and perform lithography. Okay. So, for this, after you have spin coat the photoresist, let us draw photoresist like this, you will perform the soft bake, right, you will perform the soft bake, and then process remains same. You have the mask, right, you have the mask, and then you want to etch this area. So, it will be a bright field mask. I will show you some videos which will help you to understand how the front to back photolithography works, but right now you just you understand this particular process, alright. So, this is my bright field mask, and after loading the mask, after photoresist coating, soft bake, loading the mask, what I will do? I will expose this wafer with UV. When I expose this wafer with UV, what will happen? The unexposed region will be stronger and the exposed region would be weaker. Unexposed region would be stronger, exposed region would be weaker when I dip this wafer in the photoresist developer. So, if I dip this wafer in photoresist developer, what will happen? What will happen? Let us see. My photoresist will be saved in this area, right. Next step is hard baking, right. After hard bake, my next step would be I will dip this wafer in BHF. Why BHF? Because BHF is the etchant for silicon dioxide. BHF is etchant for silicon dioxide. So, if I dip this wafer in BHF, what would I have? I would have my silicon dioxide getting etched from the area which was not protected by photoresist, right. My silicon dioxide in the area which was not protected by photoresist got etched when I dipped that wafer in buffer hydrofluoric acid BHF, alright. After this what is the next step? Next step is I would strip off this photoresist, strip off this particular photoresist. For stripping of the photoresist, what we have to do? We have to dip this wafer in acetone. So, when I dip this wafer in acetone, what will happen? My photoresist will be stripped off and I would have silicon dioxide like this. Then what I will do is I will spin coat positive photoresist in front, and hard bake it directly, hard bake. This will protect my front side, this will protect the front side. I am spin coating positive photoresist on the front and then hard bake, alright. This will protect my front side. Now I will either dip this wafer in KOH or TMAH, or this is your wet etching, right. This is wet etching, or I will use DRI, which is my dry etching. DRI stands for deep reactive ion etching, right. Either I will use wet etching or I will use dry etching to etch silicon wafer, and when I etch silicon wafer, what will happen? If it is dry etch, then I will have diaphragm which looks like this. If it is wet etch, then I have diaphragm which looks like this. Okay. So, this angle that we create is 54.7 degree, angle that we create is 54.7 degree. However, in dry etching we do not have to have the angle, cool. So, let us assume that we are using a DRI and thus we have the, we can see diaphragm like this. What is the next step after this? After we etch it, after we etch, now you should know many things in this. First is that what is the etching rate, etch rate of silicon when we use potassium hydroxide, when you use TMAH, tetramethyl ammonium hydroxide, or you use DRI, what are the etch rates of silicon, right. That is you should know. What is the temperature, because etch rate will also depend on the temperature. Once you know the etch rate and temperature, and if you can control that, means you can control that, you optimize the temperature, then you know that okay, it is like 1 micrometer per minute, right. Then how many minutes you require to etch the silicon to have finally whatever the thickness of diaphragm you have, you want for your strain gauge. Suppose this is 500 microns, your silicon thickness is 500 microns, assuming that you are using a 4-inch diameter silicon wafer, and then you are etching silicon which is about 400 microns. So, remaining is your 100 microns, the thickness of the diaphragm is 100 micrometer. That means for etching 400 micrometer, if your etch rate is 4 micrometer per minute, how many minutes you require? So, 4 and you have to etch 400 micrometer, so it will be like 100 minutes, right. 100 minutes you require to etch 400 micrometers. So, I will dip this wafer for 100 minutes in the solution if I know the etching rate is 4 micrometer per minute, correct. Alright. Now, once you have that, then what you have to do? Then you have to strip off the photoresist, So, I will take out this wafer and I will dip this wafer in acetone. When I dip this wafer in acetone, what would I have? I would have a strain gauge on the diaphragm. I will have a strain gauge on the diaphragm, right. This will be my silicon dioxide, this is silicon, this is strain gauge material, this one is my strain gauge, not any more material because we have patterned it, and this one are my contact pairs. Alright. So, we got this, right. This is how the micro machining works, in particular bulk micro machining works. Okay. So, this was about your MEMS operation. Now, let us very quickly see there are other sensors which are called inertial sensors, and in that we are talking about MEMS accelerometer, and we have MEMS gyroscope, alright, MEMS accelerometer and gyroscope. So, gyroscope can measure the angular velocity that we have applied, right. Accelerometer can also understand what is acceleration in your things, in which we can have the springs, capacitor, proof mass, and same thing goes for your sensing mass, driving mass in case of the gyroscope. Before we go to complicated structures like this, you should understand a simpler structure about fabrication. So, but I am just showing that these initial sensors we can fabricate using MEMS based technology. There are many more applications of this MEMS based technology in biomedical applications, and I think we will discuss about these applications in a next module. We will talk about all these biomedical applications in the next module. Alright. So, if we recall what we have seen in this particular module, we have seen different kind of inertial sensors, then we have seen the micro machining technique for strain gauge and how to fabricate a strain gauge, what is the process flow, the sensor types, capacitive, piezoelectric and thermal, and finally where are the MEMS used, by taking an example of Samsung Galaxy S5. Alright. So, I will stop the module at this particular moment, and in the next module, like I said, we will discuss more about how the MEMS can be used for biomedical applications, and further where it is used, like some additional applications, including it is used in cars, it is used in RF MEMS, it is used in optical sensors, and also in lot of other applications including pacemakers, implanted coronary pressure measurements, we have retinal prosthesis, we have glucose monitoring devices and many more. Alright. So, till then you just go through this particular module once again, you will understand that even it looks very simpler until you understand the photolithography technique and you understand that the recipes, it is little bit difficult. Once you understand the lithography technique and the recipes, remaining things remains extremely simple, right. If you know photolithography, you can fabricate lot of sensors and transducers. Okay. So, I will stop my module here, and then I will catch you in the next module. Till then, you take care.